Welcome back. Sorry for the interruption a little bit. I had some issues. In the last video, we were until here, where it says that find out the output characteristic impedances. So we find out our characteristic impedances, which is 150 and 75 ohm. Then we need to compute the reflection coefficient looking into the output ports. So let us continue with that. So we have 75 ohm here and we have 150 ohm here. So we're going to use these values to analyze more to find out what is the reflection coefficient here, here and here. So as we already have calculated this 75 and 150 ohm, we can use it. But first and foremost, we need to know one thing, that if we are using this port as the port of analysis, so these two ports will be connected in parallel, because this is connected in the common ground. So this and this will be in parallel. And if we look into this one, these two will be parallel, and if we look into this one, these two will be in parallel. So the equation, we know that any reflection coefficient, if you want to find from any port, so the load impedance minus the characteristics impedance or line impedance divided by the load impedance plus the characteristic impedance. So we need to find out ZL first, and then we use this value to calculate what is the reflection coefficient. So let us consider port 1 first. In port 1, we have Z0 is 50 ohm. So here it's 50 ohm. But what is the ZL? ZL is the parallel of 75 ohm with the 150 ohm here. So ZL is 75 ohm plus 150 ohm, parallel with 150 ohm is equal to 150 multiplied by 75. As you know, this one I will not elaborate more because it's electrical circuit analysis only. So after this we got 50. Now we have 50 ohm and our load characteristic impedance is 50 ohm, means 50 ohm minus 50 ohm is 0, right? So 0, anything over 0 is equal to 0. That's how we know that the impedance, the reflection coefficient of port 1 is 0. So we got one reflection coefficient for port 1. Now we look into this one. Once we look into this one, then this and this becomes the load impedance, which is in parallel. So we equate the same way that we have calculated this one. 150 parallel to 50, these two. So we get 37.5 ohm. This is a mistake, I believe, but you correct it by yourself. It's just calculation. So when we use 37.5 here, so the same equation we are using here, 37.5 minus 75, and then after that we got 1 by 3 negative. Means 1/3 of the power is reflecting back, which is undesired. Similarly, when we look into this one, we have this and this parallel. So when they becomes parallel, they give us a total of equivalent impedance of 30. Use 30 with 150 as a characteristic impedance. So we get minus 2 by 3. So now we know that there are some reflections here. Now let us see this parameter. As I already told you before, that the lossless dividers, even though they don't give any losses here in the transmission ways, but for the reflection, it gives us trouble. Reflection at port 2 and port 3 is very high. So 1/3 of the power is reflecting back and 2/3 of the power is reflecting back. It means this device will give us trouble in terms of the reflection. Now to resolve this issue, to counter this problem, we need to change something here. In this one, this is structure, this is structure. We need to change something. We're going to put resistive loads here, different resistive loads here, and check what is the effect. So that's why once we put a resistive loads here, this lossless divider becomes a resistive power divider, which is somehow like this. It will look like this. Here you can see that we have added 1/3 of the characteristics impedance of the line impedance at the each port. So these and these values are same of the 1/3 of these and these values. So this is the one change that we have made, and to do so the whole analysis become different now. So we need to change it back, and we need to analyze again in terms of the transmission and the reflection coefficient. And as we know that to find out the reflection coefficient, we need to analyze the impedance first. So we need to find out what is ZL. Since this is ZL here, you check these are three are equal, right? Same, isn't it? So this is this device is actually symmetric and also reciprocal. So if we find out what is ZL here, it means this ZL and this ZL will be the same. So let us try to find out what is the impedance in this line first. Later on we will parallel with this one. So we have Z0 here series with Z0 by 3, right? So that's how we have here Z0 by 3 plus Z0, which gives us 4Z0 by 3. So we have 4Z0 by 3 here. Similarly, this arm also have 4Z0 by 3 and this arm also have 4Z0 by 3. Now what is here now at this point? At this point, this is 4Z0 by 3 and this is 4Z0 by 3, and both are in parallel. So if they are in parallel, so we know with the same amount, if y parallel with y, then we will have a result of y divided by 2. So these are the same, right? So just dividing by 2 with this, it will give us the equivalence impedance value. So 4z divided by 2 divided by 3 divided by 2 gives us 2z divided by 3. So until here we have 2z by 3. Now what is until here now? So this is totally ZL, right? And then ZL is series with this, so it becomes what? 2Z0 by 3 plus Z0 by 3, which is actually Z0. So this is Z0, our line impedance, and the whole, we already analyzed the whole device is also Z0. So they are equal. So we know that if the impedances are equal, there will be no reflections, isn't it? Now we can say that these three are matched. check the equation here also. So ZL1 is equal to Z0. It means the reflections is 0. So from here is the same. So this is match, match, and match means there is no reflection. So reflection is gone. The issue is resolved. But now we need to check, since we have added some resistive element here, what will be effect of this in terms of the power division. Are we going to lose a lot, or the power will be splitted without any loss? To do so, we need to go for further analysis. Here we have known already, this is we have already have done, that we have seen already. This is no reflections. Now we try to find out what is the situation in terms of voltage here. These are transmission coefficients. To do so, we need to analyze in terms of voltage and impedance. So we declare here V1, a common voltage, because this is a common place for everybody. So a common node voltage of V, and then this is for port 1 is V1, for port 2 V2, and port 3 is V3. So our goal is to first find out how much voltage is coming here. Is it dropping anything here? And then we're gonna see what is the voltage here at the output here, V2. So from there we can actually assume, we can decide that how much power is actually transferring from here to here. So let us go here. We see that the V is equal to what? V is equal to the voltage across the load impedance, isn't it? And since we know already, we have calculated that until this one, the impedance is 2 Z0 by 3. So the any voltage across this one is actually V. So we have an incoming voltage of V and dissipating into this and the total ZL. So if we follow the voltage divider law, so the V we will get by multiplying V naught with this divided by this plus this. So like this here. So V1 is multiplied by this and divided by this plus this. So with this we get 2 by 3 V1. So it means that 1/3 of the power is dissipated here. So we already finding out that there are some losses here. Okay, so which is undesired, but still losses are uh, less undesired than the reflections, because losses will never destroy the source, but the reflection will keep coming and it will destroy the source. Now the next step is to find out what is V2 and V3. Since this is a reciprocal network, so V2 and V3 will be the same. If you're looking from here, if you're looking from here, then V1 and V3 will be the same. And if you're looking from here, V2 and V1 will be the same. Since we are looking at here, so we find out what is V2 and V3, which is equal. So V2 is equal to V3 is equal to actually what? Let us consider here first. This is series with Z0, right? So V2 is across actually Z0. So if we have the similar way, what we have done here is Z0 multiplied by V actually, because V is coming here. So Z0 multiplied by V, and then Z0 by 3 divided by plus Z0. Same. So it becomes 4 by 3, 4 Z naught by 3, and then when it goes, it reverses itself. This is your part to understand actually, this is easy. It becomes 3 by 4 V only. Now we know V is equal to actually 2 by 3 V1, 2 by 3 V1. Similarly, if we take out this, and this, we got half of the V1. So now we know that once we use this one, so half of the voltage, here we get half of the input voltage, that's all. So half of the voltage here, half of the voltage here. But this is in terms of voltage. If this is in terms of voltage, how much power it will bring here? Now let's go to here. So this is half of the voltage here. And if you common this one, it becomes 111. This is the parameter that I have shown you in the beginning. Now, in terms of power, what will happen? In terms of power, since voltage, we need to square the voltage if we want to find the power. So half of the V, 1 by V, half of the V actually, it's supposed to be up actually. This is the mistake I think in the book. So this is supposed to be up. So square, isn't it? It in terms what it becomes. So half of the P in, one fourth of the P in. It means the P2 and P4 will have only 1/4 of the input power. So half of the power will be lost in the circuit. To do to deal with this issue now, which is actually the half of the power is gone, even though the circuit is no reflection theoretically, but the half of the power is gone. So we need to deal with this issue also. So to deal with this issue, Wilkinson power divider has been designed. So a Wilkinson power divider is microstrip in nature. Usually, this is a microstrip Wilkinson power divider, which have an input. This is the basic structure in terms of the wavelength and the characteristic impedance. So the basic structure is there will be line here, which have a line impedance of Z0, which can be 50, 70, 80, whatever. And there are two splitting arms, each have a characteristic impedance of root over 2 of Z0. And then, which actually will determine the width, right? We learn about it that if impedance is high, this will become thin. If its impedance is low, this will become thick. So this will determine the width of this line. And the lambda by 4 line, this is the lambda by 4 length, means the quarter of the wavelength line. And this is Z0 also, and this is Z0, means this is need to terminate with the impedance of the line also. And one more extra resistive element we need to add from here to here, these two, in between these two, is of twice Z0. Means if it's a 100 ohm, sorry, 50 ohm characteristic impedance, then 100 ohm need to be added here. So this is an equal split actually, an equivalent transmission line of this one, and this is equally split microstrip form. However, I will not go so deep inside the derivation because it is very tedious and very long. Since you are already know about the analysis, so I have given you two different links and the book also. If you want to learn more about the derivation, you can go there. Okay, and you can talk with me, but in this course it will not be covered because we don't go so deep inside the theory, but we use the outcome. So if we want to design something like this, then let us do an example and we'll find out how we can design this. Okay. Now there is a design example 37.2 um, in the in the book Posher, David Posher book. It says that you need to design an equally split Wilkinson power divider for 50 ohm line at gigahertz 3 gigahertz. This is actually simple. What we have 50 ohm of characteristic impedance. Our frequency f naught is equal to 3 gigahertz. So our lambda is 0.1. So lambda, you know, C by F, right? So you have to do it by yourself, this one. So 0.1 meter is equal to 10 centimeter. So the length of these lines, as I told you again, these lines are actually 2.5 centimeter. And then the impedances of these lines are root over 2 Z naught, which is 70.71 ohm. And the R, this one, actually, we call it R actually, which is 2 Z naught is equal to 100 ohm. So this is the design. The design is done. So it's for the equally split. If there is not equally split, what will happen? Here, there is one more equation. So design a non-equal means 2 to 3 split Wilkinson power means here 2 to 3 means for 2 have a power ratio of 2 and 3 have a power ratio of 3 Wilkinson power divider for 50 ohm line at 3 gigahertz. So the solution would be like this, that if it's not equally split, then we need to use this formula. We need to find K. For K, sorry, we need to find K square actually, but in terms, we need to find out K also. So, okay. So, we use this K square, 2 by 3 here. So, 3 is what? P3, right? So, 3 by 2 actually. So, it's 3 by 2 here. Here, 3 by 2 is 1.5 and K is 1.225, right? So, we have Z naught, 50 ohm. Frequency we calculated already, 3 gigahertz. We have it's given here. And lambda we know, 10 centimeter. So the L means the distance, this one, the length of this one is actually 2.5 centimeter. Now the K we know, 3 by 2, sorry, K square. So K is equal to 1.225. So now we calculate this one. Here, we calculate this one. So Z naught by 3, ZO3, which is this one actually, which is 58.35 ohm. And similar way, Z naught is equal to K square, Z naught 3. If this multiplied ohm with this one, actually, if you multiply, you get this one. So these two are actually done. And now what is R? R is following Z naught K plus 1 by K, right? Okay, I think I have done a mistake here. This whole, I think it's wrong. You make it clear. You need to use this equation, guys. 50 multiplied by 1.225 plus 1 divided by 1.225, whatever it gives you, the value, you need to use it here. So this is, I will correct it in the report, in the slides later on when I upload it. So and then R2, this one, what you supposed to be the connection will be with 61.25 ohm and 40.82 ohm. So this is the way of the power divider so far. With this Wilkinson power divider example, we conclude our power divider lesson. In the next lesson, we will include the the coupled line, the couplers actually. We will discuss about the couplers and how to design the couplers and so on and so forth, inshallah. So that's all for this week. Inshallah, we'll bring a few more videos for next week. Assalamu alaikum wa rahmatullah.